Okay, so let's do an exercise of finding the minimal polynomial of a matrix. So let's start and we will do this one. This is our matrix. If you want to see, this is the matrix. And the idea is to solve and see and find the minimal polynomial. Now, remember that the minimal polynomial is the polynomial of the minimal degree that is monic polynomial, namely the coefficient of the largest degree um, variable in the polynomial is 1. This is monic polynomial. So it's the minimal polynomial, the polynomial with the least degree that annihilates the matrix. This is the minimal polynomial. Monic and least degree that annihilates the matrix. Okay, so I want to find this minimal polynomial. You can see that in this specific matrix, all the rows are duplicates of one another. So I can just, when I look for thinking about the eigenvalues and eigenvectors, I can understand that this matrix has a kernel of dimension 2 because when I solve ax equals 0, I can just take off 2 rows. So I have, for vector 0, I have dimension 2, the kernel is 2. And if so, there is an eigenvalue which equals 0 and its multiplicity is 2, and algebraic and geometric multiplicity. And I have another eigenvector. Now, how will we find it? We will look on the trace of the matrix. The trace of the matrix equals the sum of the eigenvalues. You can see that the trace, which is the values on the diagonal, sum it all up. So 1, 1, 2, which together is 4, is the sum of the eigenvalues. Now I said that there are two eigenvalues that equals 0, again because the kernel is of dimension 2. So, and this matrix is of order 3 on 3, so it has 3 eigenvalues totally. 2 of them we found, which is 0, and 1 is remaining. And we also know from the trace that their sum is 4. So 0, 0 plus what equals 4, and the answer is 4. So the other eigenvalue, the third eigenvalue, must be 4, and it has algebraic multiplicity of 1, and therefore it has geometric multiplicity of 1 also, because it can be more than the algebraic multiplicity. Okay, so we have two eigenvalues that are 0 with algebraic multiplicity of 2 and geometric multiplicity of 2, and one eigenvalue, which is 4. Now together they equal the trace, which is 4, with algebraic and geometric multiplicity of 1. Now, all the eigenvalues has algebraic and geometric multiplicity of 1, and therefore it means that this matrix is diagonalizable. For a diagonalizable matrix, the minimal polynomial has terms that each of them is to the power of 1. There are no repeat roots in the minimal polynomial in diagonalizable matrices. So, and every eigenvalue must be present in the minimal polynomial. So I have 0 and 4, and no one can show up twice. So the minimal polynomial will be built from the eigenvalue 0 and 4. So the minimal polynomial will be, let's call it x times x minus 4. And the characteristic polynomial is x minus 4 times x squared, because I have two eigenvalues which are 0. Let's see it. So this is our matrix. Now again, this is the trace, and I can know that there are two eigenvalues that are 0 and one eigenvalue that are 4. As we said, this is a characteristic polynomial. Must be, because we have two eigenvalues which are 0 and 1, which is 4. The logic I told you. And we have the minimum polynomial of this because this matrix must be diagonalizable because algebraic and geometric multiplicity equals for both eigenvalues. So it must be diagonalizable. For diagonalizable matrices, the minimum polynomial must be built from only no repeated roots for each eigenvalues, and as minimum polynomial in general case, all the eigenvalues must occur. So, but because the matrix is diagonalizable, every term is to the power of 1. So the minimum polynomial must also divide the characteristic polynomial, so it can be or this one or without the 2 here. And because what we said, it must be without the 2. So this is the minimal polynomial of the matrix A. So here we found the minimal polynomial of matrix A, and a little bit play with it, how we will find the a characteristic polynomial and the eigenvalues and etc. etc. I didn't do it in the general and more conservative way just to make it a little bit teachable, because showing you how to find the characteristic polynomial, we could do that in the normal way. Take a minus lambda I and solve it. The determinant equals 0 and get the characteristic polynomial, but I wanted to show you another way or another thinking way with the trace, for example. So we found the minimal polynomial, that's what's important, and that's it for now for finding a minimal polynomial of a matrix. Thank you very much. And thanks to ChatGPT for writing it down. And that's it for now. Thank you all.